Okay, this is Project Test 2, video number 4, problems 31 to 40. So a recent study examined 699 car accidents in Toronto over a 14-month period. Records of phone service providers were used to determine whether the driver was using a cell phone during or immediately before the accident. Overall, the researchers found that drivers using cell phones were 4.3 times as likely to have an accident as drivers who were not using cell phones. The results were statistically significant. This is important. All right, that means we had a very small p-value. We say that there is a difference. Which of the following can be concluded? Cell phones use increases the likelihood of a car accident, and we cannot say that. And the reason we can't, this is not an experiment, this is an observational study. We didn't force them to talk on the phones. So we can say that there's a relationship, there's an association, but we cannot say that there's causation. So we shouldn't say that. There is an association, there is a relationship between cell phone use and accidents, but not necessarily a causal relationship. That's what we like. We like that statement. There is a correlation between cell phone use and accident, but not necessarily an association. No, there is an association, right? We just said that there was an association. And these two words shouldn't be interchanged, but often are, and probably not going to be an issue. So I would say you probably could say there was a correlation, but we just said here there's definitely an association. All right. The association between cell phone use and accidents is negative. No, they said the more you use the phone, the more accidents you have, according to the study, or that's what they observed. Cell phone use causes more accidents. Sorry, we can't use the word cause. We can say there's a relationship or there's an association, but we cannot say that there's a cause. All right, 32. The weight in pounds of a full backpack and the corresponding number of books in the backpack were recorded for each of 10 college students. The resulting data were used to create the residual plot and the regression output shown below. So here we go. We have a residual plot and the regression output. I'm going to go ahead and write my regression equation. So we ended up with y hat equals 0.53x plus 10.53. More correctly, I probably should swap them, but that's fine. This will absolutely work. Then it says, which of the following is closest to the actual weight in pounds of the backpack of students for students who had 4 books in the backpack? All right. So they want to know the actual weight of 4. Well, this will give me the expected. So I'm going to plug in for the expected. So y hat equals 0.53 times the 4 books plus 10.53. All right. And by the way, once again, this is my y-intercept. This is my slope. So when I do that, 0.53 times 4 plus the 10.53, and I end up getting, we expect the backpack to weigh 12.65 pounds. But they didn't ask me for the expected, they asked me for the actual. So how am I going to get that? Well, this is where you're going to go residuals R equals observed minus the expected. Well, we know the expected is 12.65. We're looking for the observed or the actual. So what was the residual? Well, if I go over here to 4, how much does that weigh? And I'm going to say, you know what? My residual looks like it was about 2.5. So 2.5 equals the observed minus the expected. If I add 12.65 to both sides, (2.5) plus the 12.65, I end up getting 15.15 And just looking at my answer choices, my answer choice that's closest is 15. So it looks like the actual weight is about 15 pounds. And remember, residual equals observed minus expected, or actual minus predicted. All right. Okay, number 33. A regional transportation authority interested in estimating the mean number of minutes working adults in the region spend commuting to work on a typical day. A random sample of working adults will be selected from each of 3 strata. Okay, so we have a stratified, this tells us we're stratified survey, urban, suburban, and rural. Selected individuals be asked the number of minutes they spend to commuting to work on a single day. Why is stratification used in the situation? Well, we always stratify to make sure we represent every single group. All right. It's not, has nothing to do with bias. All right. Good sampling has nothing to do with bias. So we can get rid of bias. But what are we trying to do? We're trying to make sure we have the right proportions of people. I want to make sure that if 20% of the people are urban, I want to have 20% urban. If I have 50% here, I want to have 50% suburban. And if the remaining 30% are rural, I want to have 30%. So I want to decrease the variability in the estimate of the proportion. In other words, I want to make sure that they are proportionately shown correctly. Once again, if 20% were urban, that's what the actual population of my workers were, then I want 20% urban sample. If 50% live in the suburbs, then I want 50% listed in my, the only way I can do that is if I stratify and take, okay, we're gonna make sure we have 50% from this strata. And then if we have 30% in the rural, once again, the only way I can make sure that I have 30% rural represented is I take that percentage from my rural population of workers, okay? All right, number 34, a randomized block design will be used in an experiment to compare 2 lotions that protect people from getting sunburned. So which of the following should guide the formation of the blocks? Well, remember, in a block, we block them based on a similar characteristic, and ideally we want them similar as possible. And by the way, we don't randomly assign them to a block. We put males in one block, females in another block. Why? We broke them down by gender. In this case, participants in the same block should receive the same lotion. No, they should receive both lotions. Every block should receive both treatments. So participants within a block, both treatments need to be assigned. That's always the case. Both treatments, or all the treatments, must be assigned in each block. Participants should be randomly assigned to the blocks. No, you're assigned to the block based on your characteristic. If you're males, you're in the male block. If you're females, you're in the female block. Participants should be kept blind as to which block they're in. Hopefully they know why they're in that block, because it's based on their characteristics. It's blinding, it has nothing to do with it. Participants within each block should be as similar as possible with respect to how easily they get sunburned. That's what we're concerned about. Some people burn easily, so consequently, we want them to be similar as possible so we know we control for those impacts. This is a lot like the mosquito thing. We know some people get mosquito bit easily, so we want those that are easily bit in one group and those that are not in another. All right? Ideally, you would have done a pair design to control for the individual differences. A group of students wanted to investigate the claim that average number of text messages sent yesterday by students in there was greater than 100. So in this case, all right, that the average number was greater than 100. So HO mu equals 100. HA mu is greater than 100. That is what your known alternative is. You need to write those down. They will help you out. An appropriate t-test was conducted. In other words, they did it right and resulted in a p-value of 0.0853. So with 0.0853, if alpha is 0.1, I reject and I believe this. At 0.05, I fail to reject this and I continue to believe the claim. Because our p-value was 0.1 at the 10% level, it can be concluded that the mean number of text messages sent yesterday by students in the class is less than 100. No, they messed you up. They changed that word. If it was greater than 100, that would be true. But because that's what we have. But they said less. A is wrong. Because 0.1 p is less than 0.1 at the 10% level, it cannot be concluded. Yes, it can be concluded. It should not be cannot, it should be can. So this is wrong. Because our p is 0.05 is greater than 0.05, at the 5% level, it can be concluded. No, it cannot be concluded. All right, we cannot conclude that it's greater than 100. So that's false. Because p is greater than 0.05 at the 5% level of significance, it can be concluded that the mean number of text messages sent yesterday by school is less than 100. No, we never proved that. That was not here. That was not part of our test. So we didn't do that. All right. And so finally, because p is greater than 0.05 at the 5% level of significance, it cannot be concluded that the mean number of text messages sent yesterday is greater than 100, because that's what we were testing. All right. Make sure that your conclusion matches your null and alternative. When you have these problems, take a moment, write your null and alternative and go, oh, does it match? If it doesn't match, then that's the wrong answer. All right. Okay. This is also a pretty challenging problem, in my opinion. Two college roommates each have committed to donating to charity each week for the next year. The roommates' weekly incomes are independent of each other. Suppose the amount donated in a week by one roommate is approximately normal with a mean of 30. So we have mean of 30 and a standard deviation of 10. And the amount donated by the other roommate is also approximately normal with a mean of 60 and a standard deviation of 20. Which of the following is closest to the expected number of weeks in a 52-week year that their combined donations will exceed $120? Well, they actually have you doing multiple things here. The very first thing we need to do is find out the probability that they exceed 120. Well, what do we expect them to give? Well, on average, we expect them to give $90. And we just added those up very easily. It's like, oh yeah, if he gives 30, he gives 60. On average, they give 90. So this is their mean. And we want the probability that X bar is greater than 120, because that's what they said, 120 a week. I need to know my standard deviation. Well, I'm going to have to combine them, but remember, I can't add them directly. I'm going to have to square them and then take the square root of them. And if I do that, I have 10 squared plus 20 squared. And I'm going to take the square root of 500, and I end up getting 22.3606. 22.3606. So what is the probability that Z is greater than 120 minus 90? You know what? I should back up for just a moment. Here is their combined mean. That's their combined population mean. We want to know what's the likelihood that it's 120 or more. So over 22.3606. Well, the best way to approach this, or the quickest way, is with a calculator going to the norm CDF. And in the norm CDF, stat, test, second bars, norm CDF, lower bound 120, upper bound infinity, positive infinity. Our mean is 90, and our standard deviation is the 22.3606. But I get a probability, and my probability is 0.0898. They didn't ask me for the probability. They said, in a 52-week year, what is the expected combined donation will exceed that? Well, this is the probability that will. Well, the expected value would be N times P. So 52 times the 0.0898. So times 52. And that gives me 4.67. My answer that's closest is about 5 weeks. All right, about 5 weeks. If 4 had been an answer, we might have had an issue, but it wasn't. So 5 is my best choice in that case. All right, problem number 37. A university will add fruit juice vending machines to its classroom buildings if the student body president is convinced that more than 20% of the students will use them. A random sample of N students will be selected and asked whether or not they would use the vending machine. A large sample test for proportion at the significance of level 0.05 will be performed. The null hypothesis that the proportion of all students who use the vending machines is 20%. So here we have our null, HO, P equals 0.20, HA, P is more than 20%. For which of the following situations would the power of the test be the highest? Well, a couple things. What drives power? Power goes up as N goes up. So we should be looking for the highest sample size. Well, in this case, that gets rid of these. We're down to C and E. Now, let's look at our equation for this. Z equals P hat minus P naught over P naught Q naught N. Power goes up as this distance gets larger. As these two numbers get further and further apart, power goes up. So this value we know is 0.20. So I want to be as far away from it as possible. 50% is farther away than 25%. So this will give me the greatest power. In other words, the farther away it is, the more obvious the lie is. Okay. All right, number 38. Each of the faces of a fair 6-number die is numbered with one number 1 through 6, a different number appearing on each face. 2 number cubes will be tossed. Oh no. As soon as they give me 2 of something, I get to make a sample space. So here's one of those cases where I need a sample space. So I'm going to make a sample space for the 2 die. And by the way, before you take the exam, you need to do this 3 times as fast as you can. That way, if you have to do it on the exam, it'll go very easy for you. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. What is the probability the sum will be 4 given that the sum is less than or equal to 6? Well, oops. Those are the values that are less than or equal to 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have 15 values less than 6. What's the probability the sum will be 4? These are the values that add up to 4. 1, 3, 2, 2, and 3, 1. So basically those 3 values, so 3 out of 15, my answer is C. Now, to be truthful with you, that problem is not the fastest problem in the world, but it's the easy one to get right if you take the sample space approach. And it doesn't take that long. Remember, you can average 2 minutes a question. You can definitely do that question in less than 2 minutes and get it right. A study compared the language skills and mental development of 2 groups. Oh, that's important. I have 2 groups of 24-month-old children. One group consisted of children identified as talkative. They're going to be teachers. And the other group consisted of children identified as quiet. They're actually going to go out and make money. The scores for the 2 groups on a test that measured language skills are shown in the table below. So we have the talkative group and the quiet group. Now, please remember, these are 2 separate groups, okay? We have 2 separate groups. Assuming that it's reasonable to regard the groups as simple random samples, oh, this has an S, this is plural, and that the other conditions for inference are met, what statistical test should be used to determine if there's a significant difference in the average? Well, as soon as we're working with an average, we're going to be doing either a t-test or a z-test. We're either going to be using a z-test or t-test. From a z-test, we have to use the mean of the populations. We don't have that, so we don't have a z. So we know we're working with a t-test. Well, that gets rid of chi-squared, linear regression. So now we're down to these because we're working with means or averages. And I knew that because they said average. I have 2 separate groups. The very fact that I have 2 separate groups, it's a 2 sample test, all right? Because I have 2 separate groups. I have multiple samples, in this case, 2 samples. So this is a 2 sample test. Remember, a paired test, we have a before and after situation, all right? Something is tested twice, whether it's the pair that was tested twice or the individual was tested twice, all right? These, we have 2 separate groups, so 2 sample T. All right, number 40. An experiment will be conducted to test the effectiveness of weight loss supplement. Volunteers will randomly assign to take either the supplement or placebo for 90 days, with 12 volunteers in each group. All right, so we're going to have a 2 sample test. We're running an experiment. The subjects will not know which treatment they receive. At the end of the experiment, researchers plan to calculate the mean weight loss for each of the 2 groups and to construct a 2 sample T confidence interval for the difference of the 2 treatment means. Which of the following assumptions is necessary for the confidence interval to be valid? All right, so real quickly, we need random samples. Well, they're randomly assigning them, so that's good. All right. Our sample size needs to be, N needs to be greater than or equal to 30, which it's not. And since our sample size is not greater than or equal to 30, we have to check to make sure that the distributions are normal. All right. They need to be approximately normally distributed. Either we know that or we put together a box plot to check it out. All right. We have to make that condition, and we should have known that just because they had 12 and it's like, oh, that's too small to be normal by central limit theorem. So either I need to know it, they're going to have to tell me that, or I'm going to have to do a box plot, but somehow or another, we're going to have to check normality. All right.